In this episode, we take a careful, beginner-friendly walk through neural networks, not as a mysterious black box, but as a structured way to learn patterns from data by stacking simple building blocks. Neural networks show up in modern AI work because they can learn complex relationships that simpler models struggle to capture, especially when data has many signals that combine in non-obvious ways. At the same time, they are easy to misuse because it is tempting to assume that more layers automatically means more intelligence, or that a good score on one dataset means the model understands the real world. What you want, especially early in your learning, is a clear mental picture of what a neural network is doing from input to output and how training changes it. Once you understand layers, activations, capacity, and training flow, the rest of deep learning becomes far less intimidating because you can connect new details back to a few stable ideas. We will keep the focus on the high-level mechanics and on the kinds of misunderstandings that cause beginners to overclaim what a network can do. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A neural network is best understood as a function that turns input features into an output by passing information through a sequence of layers, where each layer applies a learned transformation. Each layer contains units, sometimes called neurons, that compute weighted sums of the inputs they receive and then apply a nonlinear activation function. Without activations, a network would collapse into something equivalent to a single linear transformation, no matter how many layers you stacked, which means the model would miss the nonlinear structure that makes neural networks powerful. With activations, each layer can bend and reshape the representation of the data so that patterns that were tangled in the original space become easier to separate or predict. This matters in cybersecurity and cloud environments because many signals are weak on their own, but meaningful together, such as combinations of login behavior, device posture, and unusual data movement patterns. The network is not reasoning like a person. It is learning a complex mapping that approximates how features relate to outcomes in the training data. That framing keeps you grounded in what the model actually does. Layers are the main organizational concept, and they help you describe the network without getting lost in the details of individual units. The first layer interacts with the raw input features, which might be numbers derived from events, text representations, or other structured signals. Hidden layers sit between input and output and gradually transform the data into representations that make the final task easier, such as classifying an event as likely benign or suspicious. The output layer produces the final form of the prediction, which might be a probability for classification, a set of scores across classes, or a continuous value for regression. The number of layers and the number of units in each layer influence how expressive the network can be, but they do not guarantee better learning. For beginners, it helps to imagine each hidden layer as creating a new set of features from the old ones, where the model decides what combinations are useful. In security analytics, those combinations might represent patterns like unusual sequences of access or subtle correlations across signals that are hard to handcode. Activations are where neural networks depart from being just a pile of linear algebra, and they deserve careful attention because they shape what the model can represent and how training behaves. An activation function takes the weighted sum produced by a unit and transforms it into an output that will be passed forward. Common activations are designed to introduce nonlinearity while remaining smooth enough for training to adjust weights efficiently. If you used a purely linear activation, stacking layers would not increase expressive power, because linear transformations composed together are still linear. Nonlinear activations allow the network to represent curves, thresholds, and interactions, which is essential for capturing complex patterns in real data. Activations also influence gradients, which are the signals used to update weights during training, and some activation choices can make training unstable if gradients vanish or explode. A beginner misunderstanding is to treat activations as cosmetic settings, when in reality they define the shape of the function the network can learn. In practical security use cases, stable training and sensible nonlinear behavior are what let networks learn meaningful distinctions instead of memorizing noise. Capacity is the term you use to describe how complex a pattern a model can learn, and for neural networks, it is closely tied to the number of parameters, meaning the weights and biases that can be adjusted. A bigger network with more layers and more units generally has higher capacity, which means it can fit more complicated functions. That sounds good until you remember that a model can fit noise as well as signal, and high capacity makes it easier to overfit, especially when data is limited or labels are imperfect. Overfitting is when the network performs very well on training data but fails to generalize to new data, often because it has learned patterns that are specific to the training sample. In cybersecurity, overfitting can be especially dangerous because environments change, attackers adapt, and normal behavior varies across teams and workloads. A network with too much capacity can latch onto accidental shortcuts, like a logging artifact that correlates with the label in training but disappears in production. Understanding capacity helps you see why model size is not just a performance choice, but also a reliability and safety choice. The flow of information through a network begins with the forward pass, which is the process of feeding an input example into the network and computing the output step by step. Each layer takes the outputs from the previous layer, applies its weights and activation, and produces a new representation. By the time you reach the output layer, the network has transformed the input into a prediction that can be compared to the true label or target. That comparison is expressed as a loss, which is a single number that measures how wrong the prediction was for that example or batch of examples. The loss function is not just a scorecard. It is the training objective, and the network is trained to reduce it. For classification, losses are designed so that confidently wrong predictions are penalized more than uncertain ones, which pushes the network toward better separation. In security work, choosing a loss that matches the goal matters because the cost of mistakes is rarely symmetric, even if your dataset treats it that way. A beginner who understands forward pass and loss is ready to understand how learning happens. Training flow becomes clearer once you see that learning is a loop of prediction, error measurement, and adjustment. After the forward pass produces a prediction and a loss is computed, the network performs a backward pass, where it calculates how each parameter contributed to the loss. This process is called backpropagation, and while the math can get detailed, the intuition is approachable. The model asks, if I change this weight slightly, would the loss go up or down, and by how much? Those answers are gradients, which are direction and magnitude signals for how to adjust weights to reduce loss. The network then updates its parameters using an optimization method that applies those gradients with a chosen step size, often called a learning rate. If the learning rate is too large, updates overshoot and training can become unstable, and if it is too small, training can stall or take too long to reach a good solution. Beginners often think training is about finding perfect weights, but it is more accurate to say training is about finding weights that work well under limited data and noise, while staying stable enough to generalize. It is also important to understand that a neural network does not learn one concept at a time in a neat human sense, even though we sometimes describe it that way. Early layers often learn broad, low-level patterns, while later layers learn more task-specific combinations, but the network as a whole is optimized together. The representations inside the network are not guaranteed to match human categories, and the same network can arrive at good predictions using different internal strategies depending on data quirks. This matters for explainability because you can be tempted to interpret hidden units as if they are clear detectors for meaningful concepts, when they may actually be responding to proxies or mixed signals. In cybersecurity data, a proxy might be a time-of-day pattern or a logging source that happens to correlate with incidents in the training set. If you mistake a proxy for a true driver, you may believe the model is learning attacker behavior when it is really learning your environment's response patterns. Recognizing that internal representations are learned artifacts helps you set realistic expectations and avoid overconfident narratives. A good beginner habit is to focus on behavior and evaluation rather than trying to assign human meaning to every internal feature. Another core idea is that neural networks rely heavily on the quality and representativeness of training data, because the model's learned function is only as good as the examples it sees. If the dataset is biased, incomplete, or unrepresentative of real conditions, The network will learn a distorted mapping and may fail in surprising ways. This is not unique to neural networks, but their high capacity can make the problem sharper because they can learn subtle dataset-specific patterns very effectively. In security contexts, labels are often noisy because incidents can be misclassified, investigations can be incomplete, and the definition of malicious can shift as policies change. A network trained on inconsistent labels may appear to learn, but what it learns could reflect investigator habits more than attacker behavior. That is why evaluation must consider not only a single accuracy number, but also where the model fails and how it behaves under different conditions. Beginners sometimes assume the model will figure it out if they add enough layers, but no architecture can compensate for missing signal and unreliable ground truth. Understanding the dependence on data quality keeps your modeling choices disciplined. Capacity control connects naturally to regularization, which is the set of ideas used to prevent a model from fitting noise too closely. Even before you learn specific techniques in depth, you can understand regularization as adding constraints or pressures that encourage simpler, more general solutions. One way to think about it is that without regularization, a high-capacity network may find a complicated function that matches training data extremely well, including the random bumps that do not repeat in new data. With regularization, the training process is nudged toward weight patterns that are less extreme or toward representations that do not rely on overly specific combinations. This matters in environments like cloud security monitoring because conditions drift, meaning what is normal today may not be normal next month due to new tools, new teams, or new workflows. A model that memorizes last month's quirks will generate brittle decisions and high operational noise. Regularization is not a guarantee of safety, but it is part of building models that behave sensibly when reality differs slightly from training. The lesson is that a good training flow is not just about reducing loss, but about reducing loss in a way that generalizes. A beginner-friendly way to understand why networks can overfit is to imagine the network as having many knobs, and training is turning those knobs to reduce error. With enough knobs, you can fit almost any set of points if you are allowed to contort the function enough, and the training loss can become very small. The real question is whether the contortions correspond to real structure or to accidental details of the training sample. Overfitting often shows up when the model becomes very confident on training data, but less reliable on new data, and it can also show up as a model that behaves strangely on edge cases because it has carved the space into overly specific regions. In classification tasks relevant to security, that could look like confidently flagging a normal behavior pattern as suspicious because it resembles a rare incident artifact in the training set. It can also look like missing genuinely suspicious behavior because it differs in small ways from what the training incidents looked like. The practical takeaway is that high capacity demands careful evaluation and humility in claims. A network is powerful, but it is not automatically wise. As you think about training flow, it helps to distinguish between learning the mapping and deciding how that mapping will be used for decisions. A network might output probabilities, but how you choose thresholds and actions based on those probabilities is a separate layer of decision design. A model can be useful even if it is not perfectly calibrated, as long as it ranks cases well for prioritization, but calibration matters if you treat probabilities as direct risk statements. In security operations, you often care about trade-offs, such as how many false alarms a team can review and how costly misses are. If you ignore those constraints, you may train a model that looks good on paper but produces an unmanageable workflow. This is another place where stakeholder expectations must be handled carefully, because people may want a model that produces definitive answers, while reality requires a tool that supports investigation and triage. The network's job is to provide a learned signal, and the system's job is to turn that signal into actions responsibly. Keeping those roles separate helps you explain results clearly and avoid treating the model as an authority. You should also be aware that neural networks can be sensitive to input scaling and representation, even though we are not discussing hands-on pre-processing steps here. Because networks learn through gradients and weight adjustments, the size and distribution of input values can affect how easily the model can learn stable patterns. If one feature has values that are extremely large compared to others, the network may initially focus on that feature simply because it dominates the weighted sums. which can slow learning or lead to distorted solutions. Representation choices also matter because networks learn from what you provide, not from what you meant to provide. If a categorical variable is encoded in a way that implies false ordering or distance, the network may learn patterns that are artifacts of encoding rather than true relationships. In cloud security datasets, representation errors can appear when log fields are converted into numeric forms that lose important context, or when rare categories are treated in ways that make them seem more important than they are. The main point is that training flow interacts with input meaning, and a network cannot correct a conceptual mismatch in how data is represented. Understanding this keeps your model building grounded in data understanding. Bringing the ideas together, the most important mental model for neural networks is that they are layered function approximators trained by iterative correction based on gradients. Layers transform representations. Activations introduce nonlinearity, and capacity determines how complex a function the model can represent. Training flow consists of forward passes that produce predictions, losses that quantify error, backward passes that compute gradients, and updates that adjust parameters to reduce loss over time. The power of this approach is that it can learn complex patterns across many features, which is valuable for modern AI tasks, including cybersecurity classification and anomaly scoring, where signals are rarely simple. The risk is that the same power can overfit, exploit shortcuts, and produce confident outputs that are not truly reliable outside the training environment. When you understand these mechanics, you can make better choices about when a neural network is appropriate and how to talk about its results without exaggeration. This is exactly the kind of disciplined understanding that helps you on the exam and helps you build models that behave responsibly in real systems.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.